So we'll jump in right where we left off. This was on page 10 of the chapter 10 worksheets. And we'll take a look. We want to identify for solutions. We want to identify the solute and the solvent and the solution. Being really aware of the labels, writing those labels. So in this problem, so there's a couple of things about this kind of a problem. I like to underline the numbers that matter. So we have 6 grams sample of blood. So we want to keep the label blood in there. We're analyzing it and found 5.73 milligrams of alcohol, and we will need to calculate the blood alcohol level, the percentage. So this will be a mass percent. If no units are given on the percent, you can assume it's a mass percent. And we want to compare it to the legal threshold 0.08% alcohol in blood. The blood is a mixture, so it's not even the solvent, it's the solution. The total solution is the blood. And that has, the water is probably the solvent, but it also has other particles in it. It has a lot of different solutes in addition to the alcohol that we're looking at. So the solution is the blood, and we don't have to worry about the solvent because we really just need grams of solute over grams of solution times 100%. So the solute in this case is the alcohol. So let's go ahead and plug that in. We have milligrams of alcohol. And so with these solutions problems, it's so helpful to write out the labels. Don't just let the units do the work for you. All right, and 6 grams of blood. And now we have to convert from milligrams to grams, and then times 100%. So on a number like this, it's important to keep track of whether you already multiplied by 100 or not, because the small values can be confusing. So I did 0.0955%. So when you see a problem like this, make sure that you go back and you answer the question. Was the person impaired? So yes, this blood alcohol level is greater than the criteria for impairment. But you also have to show a calculation with it to show that number. Let's get some practice using these mass percents. When you get a percent in a problem, it has a lot of information in there. Let's practice writing. Again, we want our number, unit, and label on the top, number, unit, label on the bottom. In all of these, we're going to assume that there's just 2 parts of the solution, just the solute and the water. Remember, the solution is named for the solute. So a 5% solution of sodium fluoride would have 5 grams of sodium fluoride per 100 grams total. So we could always just measure 100 grams of the solution, and then we know inside there is 5 grams of the sodium fluoride. So we could write it another way. We could say, okay, if I have 100 grams of solution, that must contain 5 grams of sodium fluoride. So go ahead and do the next one for glucose. So 100 grams of solution contains 25.0 grams of the glucose solute. It's an O. How many grams of water would be in there? This is kind of separate, right? How many grams of water would be in that 100 grams? Because it's just 2 components, we could figure out there must be 75 grams of water plus that 25 grams of glucose. So let's do a couple problems using this information. Again, when we get a large question like this, you can read it if you have time, or you can and look for the question, what mass of solution can be prepared, that's my equal sign, with 1.50 grams of dextrose, and notice this is our dextrose. So maybe I'll go ahead and write that in there. So to make this, grams of dextrose, how are we going to do that? What does that relate to? Maybe we want to write a factor that will help us. We can use that mass percent concentration and say, okay, if I have 100, the significant figures have to match. Do you see up in this section up here where I calculated the grams of water, I did addition, subtraction, so I'm going to match my number of decimal places. That's why I'm writing that. Okay, so 100 grams of solution must contain how many grams of dextrose or glucose? That is the 5.00. So that cancels our units and we're done. So just like we did up here with that factor, the units will tell us, in this case, we have to divide by the percent. Sometimes we multiply, sometimes we divide, and if you look at the units, then it makes it clear. So yeah, this percentage has a lot of information that you can. Thank you. And then we have sig figs. Yes, that's right. So let's do the next one. What mass of solute? So how many grams, and what is the solute? We're back to hydrogen peroxide. Is required, there's our equals, 250 grams of what? Grams of solution. Now that of is going to mean multiply by this concentration. And again, we'll need a factor like we see up at the top. So a mass percent concentration we can use like any kind of concentration.
Where are we getting 100 grams?
From the percent.
Oh.
Per is 1 over and cent is 100. So we can always take 100 grams, for example, and then we'll use that to write our factor, like we did up here. Each time this was per 100. Sometimes people will learn in math always to divide by 100 to use the decimal percent. In chemistry here we can see it with the units and the label. If you just think, oh, convert it to a decimal, then you might forget, did I already convert it to a decimal? Where is that 100? And what is inside the 100? Like here we looked at the water. This was the water plus the solute. So it's useful to use the units because they'll tell you what to do. And you can always just go into the lab and measure 100 grams. So it's very convenient. It seems almost like magic. Like how do we just know this? Because we measure 100 grams. Looks like we've got, how many more? We've got 2 more in the mass percents. How many grams of water? Here's our is. Here's our solute. And here's our percent solution. So we might want to just write that immediately in a form that makes sense, that's going to help with our problem. So maybe write a factor there. So that is per 100 grams total. But look what we want. We want water. So can we get a factor that has water in there? right? So 100 grams total means that we must have 90 grams of water, and that would make the 100 grams total. So we could use that. Or if you approach it a different way, we could do it a different way too. So 5.00 grams of magnesium sulfate. This is Epsom salts. This is what you buy in a big box to put in the bathtub. Epsom salts. All right, we need to cancel out grams of magnesium sulfate, and we could either go to solution and then figure out how much water. Let's use this factor right here, and to use it we're going to flip it. So 10 grams of magnesium sulfate to 90 grams of water, and now we can see that we're done, right? We've got water equals water. All right, so 45. And we need one more decimal place. 45 grams of water for 5 grams of magnesium sulfate. Now, I think that it's also used to drink that as a medical treatment, I think for constipation. So in the bathtub for your muscles or whatever. Anyway, 5 grams of magnesium sulfate salt in 45 grams of water. Obviously not big enough to take a bath in that. Okay, this next question says explain. We want to do our calculation, right? So we do need to calculate the mass of the solute, how much baking soda do we put, and how much water do we put in there. And then we want to use words to put it together. So I'll give you a second to do the calculation. So when we want to measure our amounts to make the solution, we will go ahead and use all of the digits that we need on the balance. We would never just make it less correct because of our sig figs. We need 2 sig figs, but if we measure out enough to get 4, that's good too. So we can see from the units, that gets us to the grams of the solute. How much water do we need? We only have 3 significant figures in that water calculation, but we would want to keep it as accurate as possible. It's very easy to measure the 0.75 grams. So we would try and measure it precisely just to make a really accurate solution. So we might make 7.50% baking soda, which is great, no problem. So let's put it together with our words. There's a couple ways you could do it. We could say and add 138.75 grams of water. Yeah, that works. What we do not say is add 150 grams of water because then our total will be too high. Okay, in the next section, I'm going to just outline how it works. The calculations are the same. In this case, we have a mass volume. So we're going to assume milliliters on the bottom. So a mass volume is grams of solute over 100 milliliters total. Now this we see, for example, with some beverages like beer or wine coolers or vinegar is often a weight volume percent given on the bottle. And it will say that. It'll say mass volume. We also see it sometimes with our solutions that you might encounter in the health field. So this is a saline solution, maybe for an IV. Sometimes those will be mass volume. It works exactly the same way. But instead of 100 grams below, we put the milliliters. I want to move forward and make sure we get to some of the bigger conceptual problem solving, and we can come back to this if we have time, if you have questions. But maybe you could work these on your own and then ask questions, and that would be one way to check in and make sure that it makes sense. I will probably only ask mass percent questions. But these are nice examples, again, because clindamycin is antibiotic. So you'll see these in the grocery store, and you might see these in the health science fields. Dilution, though, I wanted to make sure we get to dilution and have plenty of time for these problems, because the pre-lab for Monday includes one of these problems. When we have a dilution, we are just going to change the volume and the concentration. We're not doing any reactions yet when we do a dilution. My favorite way to think about this is when you buy hot chocolate at the coffee stand. I don't know who gets to go get coffee anymore. But I used to talk about the buzz at Seattle Central. If you buy a hot chocolate, they have the little pumps of chocolate. And they take your small cup and they put 2 pumps in it. And then they add milk. So we want to drink the chocolate at a certain concentration, right? So we have the concentration we want to drink. And we have the more concentrated solution, the stock solution is in that pump. And maybe they do 2 pumps of syrup for the small chocolate. Maybe they do 3 pumps for the large. And then they just fill it up with milk. So in the end, we want to drink the same concentration of chocolate, but they're using, this is the stock solution, which is concentrated. And then in chemistry, we're always diluting with water. With hot chocolate, they usually dilute it with milk. Hopefully that makes sense. They put enough chocolate for the size of cup, and then they fill it up with the other stuff. And that way you get the same drinkable concentration. The way that works for our dilutions in the lab is, for example, this is 100 milliliters of stock solution. So that is the more concentrated one. You see it's dark yellow. Then they're going to put that in to the bigger flask. This is 1.00 liters. And then they're going to fill it up to the line with water. In this case, we're looking at potassium dichromate. And all of the solute that we added is in here. And that same amount of moles of solute is in here. What has changed is that we added extra water, and that changed both the volume and the molarity. We can represent this with the dilution equation. M1V1 equals M2V2. It doesn't matter which one you label as which thing, but we could say, let's see, M1 is our stock, so this side is in there. Now at the end, we have a larger volume and a lower concentration, right? Nobody goes and drinks the syrup of chocolate. We don't want to drink that concentrated one. So this side is now in there. It's a larger volume and a lower concentration. So when we have this, we're basically saying moles that we started with of the solute equals the moles in the diluted case, right? We put all the chocolate in, we make it taste the way we want, and then we drink it. But the pieces of chocolate have not changed. So we're going to use this dilution equation, M1V1 equals M2V2, and we can use a mass percent instead of a molarity, but we'll be using molarities in our lab. Okay, so let's identify the numbers. We have 100 milliliters and it's connected by the of. That means we're going to multiply. So make sure the volume and the molarity that are connected are the ones that get multiplied together. Then here is our equals sign is transferred to a larger flask, right? So that's going to be our V2. If you have 3, you're usually going to calculate the 4th one. Okay, so calculate the concentration. So that is M2. M1 equals 0.1, V1 equals 100, V2 equals 1.00 liters, right? So make sure you keep track of that unit. And then M2 is what we're looking for. Notice in this one you do not need to do the volume conversion because those milliliters just cancel out. So you can just work in milliliters. It's useful to notice that the new molarity, it's diluted, it's always lower than the original one. So there's a good ballpark check.
How many significant figure we're gonna use this?
This one is going to have 3 because of this number here and this number here. So I'll write that equation. In this next one, we're going to use a mass volume percent. So we'll just use the same equation, but we can call it C1V1 equals C2V2. We'll just use that same dilution equation, but now we have these units will stay the same, right? They'll just cancel out. Now make sure that you're always grouping the ones together that are connected by that of in the problem. The usual mistake is that we switch 2 of them. So we'll take a small amount of the higher concentration and we're going to add enough water to bring it up to 1 liter. Right? So that's how we would make that. Again, it says explain. So we want to be careful with the language. How we use our language here matters. So we're going to measure 180 milliliters of the stock solution. That's the 5.00%. And add, we could say enough water to make 0.0000 liters total, or we can give that amount of water. Take a look at the pre-lab, the Kinetics Pre-lab. That has this kind of a calculation. Maybe I'll go ahead and open that up to take a look together So everybody knows where to find this file. In the lab section, you can get it from the calendar. This is our pre-lab. So in the first one, you're going to use a mass and a molar mass to get moles, right? So we've seen these things, now we're applying them. So let's see, we have calculate the mass. So how many grams, and then you need to do the formula, equals, and then we're going to use this. Now this is where our new material is. We have a new way to find moles, right? So that's what we're doing here. So don't forget that that is going to be 100 milliliters of 0.0200 moles on top, liters on the bottom. So maybe I should draw that longhand to show you here, because I want to put that liters down here. Right, moles on top, liters on the bottom. So that's how we'll do that first one. And then down here in the next one, we're going to use the same thing that we did today. This is one solution, and this is the solution we're making. Okay, so we're going to dilute it. Notice that this one is a larger concentration. This is the smaller concentration. So we expect to take some of this, a smaller amount of this, and dilute it to make this one.